Assalamu alaikum, Physical Geology, Chapter 2, Plate Tectonics, Continental Drift, presented by Khalid Al-Amrouni, PhD in Geology, Texas A&M. Khalid Al-Amrouni is a staff member at the Department of Earth Sciences, Yunus University, Benghazi, Barga State, or Cyrenaica State. The reference used is Essentials of Geology. This is the Department of Earth Sciences at Yunus University, and this is the main entrance of Yunus University. This is the Prince of Cyrenaica State, Idris Sanusi, and he's the founder of Yunus University. And here the flag of Cyrenaica State behind the Prince Idris. And this is the commander or the chief commander of the Sanusi army, Omar al-Mukhtar. This is the capital, Benghazi City, capital of Cyrenaica State, and this is the map of Barga State or Cyrenaica State. Outlines review. Continental drift. Pangaea formed, or Pangaea, 200 million years ago, then broke up. And we'll look at the fate of the continents, fossil evidence, and then Wagner proposed two possible energy sources for drift, the tidal influence of the moon, and continents broke through the oceanic crust. Both wrong. And the correction came through the plate tectonics, which is a modern version of an old idea, continental drift. They did that through seismic activity, volcanism, mountain building, that occurs along dynamic margins. And then we'll study plate tectonic boundaries, 3 boundaries based on their motions, different divergent boundaries, convergent boundaries, transform fault, and then we'll study plate tectonics and paleomagnetism, polar wandering, earthquakes, hotspots, the driving mechanism. First thing, the review. We know now from the introduction that the Earth is not homogeneous, and it has 4 different shells. The inner core, which is very solid, iron rich, the outer core, molten material, and then mantle, and the last thing is the crust, the very thin crust. The inner core about 1,000 kilometers in radius. The outer core is 2,000, and the mantle is about 3,000 kilometers. So in total, there's 6,000 kilometers. If you compare it with the crust, which is 5 to 40 kilometers, the crust is about less than 1%, almost 0.5% of the total of the thickness of the whole planet. And here we have 2 important zones, asthenosphere and lithosphere. This is just a section taken from the uppermost mantle to the crust. So the uppermost mantle, the 600 kilometers here, we call it asthenosphere. It's a hot, weak, capable flow zone or capable flow. And then above it, there's rigid zone made up of the uppermost mantle and the continental and oceanic crust. And this, what we call it, lithosphere, the upper 100 kilometers. And now we're talking about the driving mechanisms or the forces. So the basic idea is convection cells. This is the simplification of convection cells. When you heat up the water in the pot, the hot water will rise up, and then when it comes to the top here, it cools down and then sinks under the buoyancy force. And this is exactly what happens in the convection cells. So the rock material in the mantle, they're hot and lighter under the buoyancy force, will go up, float up, and extrude through and create fractures and extrude through some volcanoes here, and the rest will keep moving around here and dragging the lithosphere, and then cools down and sinks down again, and then heats up and keeps floating under the buoyancy force, and on and on and on. This is called large convection cells. Some other scientists, they said no, the convection cells just restrict to the upper mantle. Some other they said no, this is through some areas and called hot plumes coming from the mantle, but still spreading around as convection cells. So these are the three driving forces of plate tectonics. So how the breakup or the fragmentation of the crust or the lithosphere happen. So here we have an example from Africa, East Africa. We call it Afar lowland or Afar rift. Here we have three arms: Gulf of Aden, Red Sea, and the third arm goes through the Afar rift. This configuration here, like Mercedes-Benz shape, we call triple junction. What happens at first? The whole area heated up and formed a dome. And then after that triple junction configuration happens, two arms, this and this, will open up, and one of the arms, the third one, will fail and stop opening. And these two arms here, they represent Gulf of Aden and Red Sea. And the third arm, the one that failed to open, is the East African rift or Afar lowland. This is the main idea of triple junctions, and here we can see it on the map. 1, 2, 3 arms, and this is the triple junction. This inside here, the triple junction, these the ocean ridges, opening areas, creating a new oceanic crust. And this on the sides will be subduction zones in the future. This is the main idea of triple junction. And these triple junctions happening on the continental crust. And here we see that the plate or the lithosphere is fragmented into small plates due to the uneven distribution of the Earth's heat. And here we have African plate, South American plate, North American plate, Eurasian plate, Arabian plate, Pacific plate, and Australian Indian plates. And each plate has or moves by, on its own, and they have boundaries, dynamic boundaries here. The blue ones here, they represent conversion zones. The red ones here, they represent diversion zones. They open the plates away from each other, conversion the plates against each other. And the green ones represent transform faults. And here we'll see again that plates not only fragmented due to the uneven distribution of heat, they always sit in motion due to the same reason. And the average rate of motion is 5 centimeters per year, either away from each other or towards each other or sliding by each other. So plate tectonics, some facts. The position of the land masses are not fixed. Yes, plates are moving. The continents are gradually migrating. Yes, they are migrating over the surface of the globe, correct. About 5 centimeters per year. And the splitting of the continents, continental blocks, will form new ocean basins, correct. And that's what we see when the triple junctions create that drifting and keep opening, create divergent zones. And then we'll get the third thing, that we have area where we create a new oceanic crust, the divergent boundaries. We have another area where the old oceanic crust is destroyed. We call them subduction zones. And if the crustal or the continental crust collide, they form mountain ranges. And this theory, the plate tectonics theory, used to be called continental drifts. So how they discovered this? that continents used to be together and then they split apart. That happened during the or due to the observations by Wagner. He find he got like few observations, and during his time there was like no way to find out the mechanism how this one continent, the Pangaea, just split apart, broke up, and the continents split apart, and now they are split by wide oceans. So continent drift suggested, or continental drift suggested, that supercontinent Pangaea, which means all land about 100 million years ago, then broke into smaller continents, which then drifted to their present position. So, what's the observations? If you look at South America and Africa, they can fit. You can match them together and fit. This is first observation. Second, ancient climate similarities. Here, 300 million years ago, we had ice age, and that affected all these continents: Africa, India, South America, Australia, and these places, and then the southern pole. These places still have sediments of the same ice age. Now they are split apart, but 300 million years ago they used to be together in one continent, Pangaea. And the third evidence is the fossil evidence. These fossils in South Africa and South America, they are the same. They have the same age, the same kind of fossils, the same species, but they are way far away, spread away right now. But they used to be one continent. For rock structure, if you look at the Appalachian here in the U.S. and the Caledonian Mountains, they are far away, but they used to be one chain or one range of the mountains, the same rock type, rock age, and it used to be the same mountain range. So this is just zoom out or zoom in of the same figure. And now Wagner, he was trying to find a mechanism or energy source for the drifting. He said the tidal influence of the moon, that's not enough. And then the continents broke through the oceanic crust. He was thinking the continental crust riding over the oceanic crust, which is completely not true. So the plate tectonics, the modern version of the old idea continent drift. What they find out, the outer rigid lithosphere consists of rigid segments called plates. Correct, yeah. We have plates like South America, North Africa, Pacific, all of these, like Eurasia, North America, all of these plates, segments. The plates contain both continental and oceanic crust. So the plates, which is the lithosphere, has continental, oceanic, and the uppermost mantle, lithosphere. This is a major departure from the continental drifting theory, which proposed the continents move through, not with, the oceanic floor. Plate tectonics said continental and oceanic plates, they move together as one unit, not the continental riding over the oceanic. And each plate moves as a distinct unit in relation to other plates. This is another fact. And then the other fact, all major interactions between plates occur along plate boundaries. So that's when we got the plate boundaries. And that's where most of the Earth's seismic activity, volcanism, and mountain building occur along these dynamic margins. They call them dynamic margins. The divergent zone, conversion zone, and transform fault. Okay, divergent zones when we have magmas upwelling and breaks through the continental plate and keep pushing the plate, the two sides of the plate away from each other, and it creates a new oceanic crust. This is diversion. This is the area of creation of new oceanic crust. The example is the Red Sea, or Rift Valleys, Red Sea, and Mid-Atlantic ridges. Here we have convergent boundaries. In convergent boundaries, they create subduction zone where two plates move together, causing one of the slabs of the lithosphere to be consumed into the mantle as it descends beneath an overriding plate. So one plate overriding the other one. And here the destruction, convergent boundaries, destruction of the old oceanic plates. The third one is the transform faults. Here there's no creation and no destruction, just plates slide past each other without creating or destroying any lithosphere. Just what happened, just deformation. And San Andreas fault is the famous example. Here again shows us the zones of divergent boundaries, the red ones. Any red zone here on the map, divergent. Plates running away from each other. Zones of convergent, where plates, one of them riding the other, and creating subduction zone, that's destruction of old oceanic crust. And the green, this is the blue zone here, blue lines. The green zone is transform faults. Transform faults, we call them transform faults because along them, the motion changed from conversion to diversion. So they connect diversion boundaries with conversion boundaries. So these three different ways of movements. So when we have divergent boundaries, eventually the ocean basin and ridge system will be created. So the process just warps the crust, warps up, and then creating rift zone, rift valley, and then narrow sea like Red Sea, and then ocean basin like mid-Atlantic ocean ridges. Let's look here. So this is one of the arms in the triple junction. What happens here? As magma upwells up, will heat up the area and creates domes. It's called upwarping, and then creates a lot of fractures. As the magma comes through and pushes both sides away, that will widen the area, and this dome will collapse down due to the widening, the more space, and the magma will keep pushing up and pushing both sides away and widening the continental rift, like Rafah Rift in East Africa, until it gets to the next stage, which is the linear sea and oceanic crust created in the middle here. Linear sea, the most famous example is the Red Sea. And then after that, the magma will keep upwelling and creating new oceanic crust and pushing both sides away from each other of the lithosphere. And that will create mid-ocean ridges like Atlantic Ocean. And this is it's called the seafloor spreading process. But at some stage, one of the sides of this ocean will break, or both sides will break, and create subduction zones. And this leads us to the convergent boundaries. And these convergent boundaries could be oceanic with continental and creates trench, and continental volcanic arc. And the old part of the oceanic crust will be destroyed, or sometimes between two oceanic crusts, and that will create volcanic island arcs, so islands inside the ocean. And if two continental crusts collide, that will create mountain ranges. And this is the whole cycle. We call it Wilson cycle or tectonic cycle. It talks about the opening and closing of the ocean. So the first part, upwarping, a boiling of magma, pushing it up, and then collapse of this fractured zone as the distance widened and the space widened and more pushing away and more magma coming in the middle of wells, and then until it creates a new oceanic crust and creates, this is rift stage, rift valley stage, and then creates linear sea like Red Sea, and then keeps opening and pushing both sides away, both continental sides away from each other until it creates creates an ocean basin. And this middle part we call mid-ocean ridges, like Atlantic Ocean. And then when one side fails, or both sides fails, of the oceanic crust, that will create subduction zone, and now we'll start the reverse process. The basin will start closing and narrowing down until both sides of the continent just collide and forms mountain ranges like Himalaya now. And this closing stage is the Pacific Ocean. Now it's at the closing stage because it has these subduction zones. Transform faults, fault boundaries. Transform faults, larger fractures, connected, converging and diverging plate boundaries into a continuous network that divides the Earth's outer shell into several rigid plates. And most of transform faults are located in oceanic crust, but few, including the San Andreas Fault in California, are situated within continents. And this is San Andreas Fault. San Andreas Fault connecting conversion boundary with diversion boundaries. Right here in California. Plate tectonics and paleomagnetism, polar wandering, earthquakes, hotspots, the driving mechanism. Okay, the plate tectonics and paleomagnetism. Paleomagnetism, we have magnetite minerals, mainly rich in iron. These minerals, they obtain, above 580 degrees Celsius, which is the Curie point, they lose their magnetism. Below it, they obtain their magnetism. So when the magma cools down below 580 degrees and we have magnetite minerals or iron-rich grains, these grains and minerals will obtain the magnetic field or the Earth's magnetic field at the time of their formation. And once the minerals solidify, the magnetism they possess will remain frozen in the position. And that's what we call it fossil magnetism or paleomagnetism. If the rock is moved or the magnetic pole changes position, rock magnetism will retain its original alignment. So it doesn't matter what happens after. These rocks with the paleomagnetism will keep their original direction. So here we have polarity at the mid-oceanic ridges. We know mid-oceanic ridges, new magma is common. So the red old one, new one is, the white one is the new. So this normal polarity, as you go in the stage, another magma, the old one, the normal polarity will go away and another polarity will come up, new magma, and obtain a new polarity we call reverse. So the normal polarity, when the the magnetic directions is the same as the today's magnetic field direction, and if it's not, we'll call it the reverse polarity. So polar wandering, the Earth's magnetic field is generated by the rotation of the Earth about its axis. Okay, and the Earth's magnetic field periodically reverse polarity. Also, the Earth's magnetic field changes intensity and weakened over time. And when that happens, it becomes weak, sunspot activity could possibly contribute to a reversal of polarity. So this is the polar wandering. And, when, as they said here, this is a clear evidence that either the magnetic poles had migrated through time, which is impossible. This is the ancient idea known as polar wandering, or the continents had drifted, which is the true assumption that continents had been drifted. So here we have apparent polar wandering path for Eurasia. This is the present day, present geographic position. And this is apparent polar wandering path of North America, 100 million years ago, 200, 300, 400, 500. So when they tried to match them together, these paths, what happened? What they got? They got the same geographic configuration of Pangaea or Pangaea. That means the plates are moving. Plate tectonics and earthquakes. So the deep focus earthquakes are confined to subduction zones or oceanic trenches, while earthquakes with along the diversion boundaries and transform faults are shallow. The focus is shallow. Here from Japan, as we go, this is subduction zone. This is the Japanese here, this one here, and this is China mainland. So subduction zone going this way down. It's taken here. As you go down here, the blue dots, shallow, yellow, intermediate, and red dots, deep focus for the earthquakes. The only places they find earthquakes, deep earthquakes, is subduction zones. And this way they can map the depth of the descending slab, the asthenosphere. Hotspots. Hotspots is one of the mechanisms of the distribution or the uneven distribution of the heat in the Earth's interior. And here, they discovered those hotspots where they find decreasing age of volcanic activity towards Hawaii. So here they find out there's this island here, 3.8 to 5.6. As you go this way, the age is getting younger, 2.2, 1.3 million, less than 1 million, and 0.7 to present day. This is still forming Hawaii. That means all of these islands, they move it above hotspot. So the first island, this one, the volcano is extinct, but Hawaii is still active, the volcano. So this island was under the hotspot, was right here, and then move it forward. The second one formed, and then move it forward. The third one formed and moved forward, and then the Hawaii formed. So like 3.8 million years ago, this island was here at this location of, of Hawaii. But what made this island to move from here to there is the plate tectonic movements. The plates are moving this way, and the hot spots are stationary, as explained here. Hotspot volcano stationary, and then this one will move forward, and new one comes, and new island will form. So the driving mechanisms, proposed models of the driving force for plate tectonics: large convection cells, number one; number two, convection cells confined; number three, hot plume model. So what's large convection cells? Large convection cells in the mantle carry the lithosphere as in a conveyor belt fashion. Two, convection cells confined to the mobile upper mantle are responsible for the plate motion. Push-pull models are also a type of convection cell. Here, the cold, sinking oceanic slabs pulls the trench seafloor along, while gravity, that's conversion, while the gravity sliding of the material down the elevated ridge crest pushes the slabs. So this is for gravity for the divergent boundaries, and the sinking for the convergent boundaries. The hot plume model suggests that all upward movement is confined to few narrow plumes, while downward flow occurs slowly throughout the remaining mantle. So the downward movement, they mean the subduction zones. And these are the three models again: the large convection cells, slab pull, slab push, and the hot plume. And the summary, we have continental drift, which is now they call plate tectonics. And the idea started with the Pangaea 200 million years ago. Then the Pangaea broke up. How they discovered the fit of the continents, fossil evidence, fossil and mountain builds, paleoclimate evidence, glacial deposits. Wagner proposed two sources of energy source for the drift: the tidal influence of the moon. Continents broke through the oceanic crust, both wrong, not correct. The plate tectonics theory came in and corrected his ideas. And the plate tectonics, they discovered plate boundaries through seismic activity, volcanism, mountain buildings, and they find them dynamic margins. Plate tectonics found out there are three different boundaries based on their wave movement: divergent boundaries, convergent boundaries, transform faults. And the divergent boundaries, they create ocean basin and ridge system, and they're plate spreading, and they and they create new oceanic crests. Convergent boundaries, sites of destruction, collision, and they destroy old oceanic crusts. And then transform faults, most of them in oceanic crust, but few of them situated within continents. Plate tectonics and paleomagnetism, the Earth's magnetic field, Curie point, magnetite minerals, fossil magnetism, and paleomagnetism. Polar wandering is the clear evidence that either the magnetic pole had migrated through time, which is an ancient idea called polar wandering, or the continents had drifted, which is the correct thing. Plate tectonics and earthquakes, deep focus earthquakes confined to oceanic trenches, subduction zones. The others, divergent and transform faults, always shallow focus. And then we went to hotspots, and then which are stationary, and then the driving mechanism models for plate tectonics, large convection cells, and convection cells confined to the upper mantle, which is push and pull, and then the hot plume model. And then by this, we came to the end of this lecture, the take-home message. And now we get 3 minutes rest and listening to the national anthem of Saranac State. يا أيها العالم النظير يحيى الأمير يحيى الأمير رفرف فأنت شعارنا وإلى الأمان منارنا بك أغلقت أبصارنا وإليك بالفخر نشير يحيى الأمير يحيى الأمير بالأمس جاف رابط واليوم قد عان المسير يحيى الأمير يحيى الأمير العلم نور حياتنا والدين خير هداتنا والصبر سور صفاتنا والله مولانا النصير يحيى الأمير يحيى الأمير. Thank you very much.